Hello everyone, I'm Shabbir Shaikh. I'm a postdoc at Arizona State University. I will be talking about cosmology from cross-correlation of ACT-DR4 CMB lensing and DES-Y3 cosmic shear. People mentioned here are main collaborators in this work within larger ACT and DES collaboration. This is a in preparation work currently undergoing collaboration review. Hence, most of the results that I will discuss are either from simulation or from blinded data. Let's begin. Radiation from cosmological sources, such as galaxies and the CMB, is gravitationally lensed by the intervening matter between the sources and the observer. In most cases, the deflection is small, falling within the regime of weak gravitational lensing. For example, in case of CMB, it is of the order of 1 arcminute. Knowledge of this deflection field allows us to reconstruct the matter that is doing the lensing. Moreover, for in a given direction, so the lensed CMB and the lensed galaxies are lensed by some of the common matter. Hence, their lensing signatures are correlated. Hence, it is interesting to look in the correlation between the lensing of these two sources. In case of CMB, the lensing of CMB manifests as distortion of hot and cold spots. The left panel here shows lens CMB temperature anisotropies. The central panel shows the difference between two. As you can see, most of this difference arises at small scale. However, these changes in the CMB anisotropy are correlated. And these correlations allow us to reconstruct the lensing potential that is doing the lensing. The right panel here shows the lensing potential that is lensed. This CMB anisotropy is shown here. One thing to note here is that these lensing deflections are correlated, and this correlation scale is of the order of few degrees, and that is due to the scale of the lenses that is doing the lensing. So the right panel shows the lensing potential. The arrows here shows the gradient of the lensing potential, which is actually the deflection caused by the lensing. One way to look for the CMB lensing signature is to look into the correlation of the Fourier modes of CMB temperature anisotropies, and that allows one to reconstruct either the CMB lensing potential or what is called convergence, lensing convergence. This lensing convergence can be written as a weighted sum of the matter density contrast. So the W is generally called lensing weight. In case of galaxies, the manifestation of lensing is the distortion of the shape and the correlation in these distortions. To a good approximation, the observed galaxy shape can be modeled as the intrinsic galaxy shape plus the shear distortions. Now, assuming the intrinsic galaxy shapes are randomly oriented, on an average, the galaxy shapes are then the measure of an average shear signal. Shear and convergence are related. E mode of the shear field is proportional to the harmonic modes of the convergence. Hence, in this way, shear is also a measure of projected matter distribution. The lensing contribution depends on the lensing weight. In case of CMB, which is a lensing source at redshift of 1100, the lensing kernel is quite broad, as shown by the red curve. For the galaxy distribution, shown here by a dotted curve, the lensing weight is shown by a black curve here. Now, in cross correlation, what matters is an effective product of these two kernels, which is shown by the blue curve. As you can see, the combination of these two probes, different effective redshift than either of these particular observable. One way to model the correlation is to look at the cross power spectrum of the lensing of these two sources. It depends on the matter power spectrum, and through it, it allows us to constrain the clustering of matter distribution through either the parameter sigma 8 or S8, which is combination of omega m and sigma 8. Moreover, the tomographic nature of measurement allows one to reconstruct the growth of matter distribution as a function of redshift. Some of the recent studies have shown that the S8 inferred from CMB and the galaxies, so-called lower redshift measurement or observations, are in somewhat disagreement, and that is an interesting motivation to study the weak lensing in general and the cross correlation between CMB weak lensing and the galaxy weak lensing. The measurements of CMB weak lensing and galaxy weak lensing have increased in precision over the last 1 decade. So the measurement that we are discussing, the ACT-DR4 cross DES-Y3, is at a signal to noise ratio of around 7. The common sky area between these two surveys is around 450 square degree, as shown by the footprint plot here. The newly prepared ACT-DR6 lensing map nearly overlaps with most of the DES-Y3 footprint, around 4,000 square degree. That gives us a 4% precision measurement of this cross power spectrum. ACT-DR4 kappa maps are obtained using ACT observations at 98 and 150 gigahertz. ACT prepared two flavors of kappa maps, one using ACT only measurements at 98 and 150 gigahertz bands, and the other one uses also Planck frequency channels, where any contamination that is coming from thermal SG signal that is present in CMB observations is deprojected. This deprojection of thermal SG signal is required because especially important for cross-correlation studies, because thermal SG signal also probes the large-scale structure. So any contamination in the CMB lensing map arising from thermal SG signal correlates with any other probe of large-scale structure that has a similar redshift overlap. And then this can cause bias in the cross-correlation. This bias has been shown to be of the order of 10%, depending on the redshift one is talking about. So mitigation of the thermal SG signal is in the kappa map is important, and we used one such map where SG signal has been mitigated. So in principle, what we are doing is we are taking reconstruction of a mass map obtained by ACT and correlating with a measure of mass map, not exactly mass map, but the shear map obtained by DES, and correlating these two fields. So the red panel here shows the same sky patch where ACT obtains its CMB lensing reconstruction. A quick look at the analysis procedure. To model the angular power spectrum of the cross correlation, we use HaloFit to get the matter power spectrum. We use simulations to obtain the covariance matrices for the statistics, where we model kappa and the shear signal gamma as correlated log normal fields. To these signal maps, we add the respective lensing reconstruction noise of kappa and the shear measurement noise obtained using DES-Y3 catalog. So we generate 511 of such simulations to obtain the covariance matrix. We do not carry out all measurement over all the harmonic modes that are available. In fact, we need to take into account something called mean field bias in CMB lensing reconstruction that arises due to incomplete sky coverage and other non-idealities in the data. Hence, we throw away the mode below L of 100. At higher multiples, the effect of baryons needs to be taken into account. Since we are not modeling the effect of baryons in the power spectrum, we throw away all the modes above L of 1900. We carry out certain null tests to check for the non-idealities in the data. We correlate our kappa map with B modes of the shear to check for any correlation between the spurious B modes and the kappa map. We find that this measurement is consistent with 0 with reasonable PTE. We also correlate the kappa map with the rotated shape catalog shear maps. And we find that this measurement is also consistent with 0 with a reasonable PTE. These are the data band powers obtained from the blinded data. This is a look at the kind of cosmological parameters that we, kind of cosmological constraints that are expected from this data. So here I'm showing you the posterior distribution obtained using simulated data for the set of cosmological parameters. So the black curves here show the prior distribution in the space of these cosmological parameters. The blue curves and the contours show the posterior distribution of these parameters. From this, we get that the error bar on ACT that we expect from this measurement is around 0.06. We carry out this inference exercise using the parameter inference module in the SO-Light, which uses the Kobaya Monte Carlo sampling framework. Along with the cosmological parameters, we also vary certain astrophysical nuisance parameters and observational nuisance parameters. One of the main astrophysical nuisance parameter that needs to be taken into account is related to the fact that galaxy shapes are not just randomly oriented, even in the absence of weak lensing. Due to environmental effects, galaxy shapes are aligned. So that causes an additional signal in the shear correlation. That is model. So we use nonlinear linear alignment model to model intrinsic alignment. That is doing that means changing the lensing kernel by the expression shown here. There are two model parameters. One is amplitude A and the redshift evolution parameter eta that we need to take care of. So from the simulated data, what we see is that the inference on cosmological parameters does depend on the model and the prior distribution assumed for these parameters. So here, the blue contours and the curves show the constraints obtained using the fiducial intrinsic alignment prior, which is shown by the black curves here. Whereas using a wider prior does lead to the degradation of constraint on ACT. We also vary the nuisance parameters related to weak lensing observations. That includes photometric redshift bias and the multiplicative shear bias. However, we see no significant constraining power for these parameters when we are using ACT-DR4 and DES-Y3 data, which is likely to, the situation for these parameters is likely to increase with the ACT-DR6 data, which has more signal and the cross correlation with the DES-Y3. So here is a quick summary. So cross correlations offer a way to constrain cosmological parameters that are robust to some of the systematics affecting individual probes. Combining different probes alleviates some of the parameter degeneracies. Combining galaxy weak lensing with CMB weak lensing probes effectively higher redshift range, not accessible by the galaxy survey on its own. So the current measurement is at the level of signal to noise ratio 7 with error bar on ACT, which is of 0.06 and expected to increase around 3 times more SNR with the upcoming ACT-DR6 kappa map. Thank you for your attention.